So today we're going to go over 6.2, and it's our first development of volumes. And we're going to cover two types of volume. We're going to talk about the disk method and the washer method. And the distinction between the two is a disk you can think of like a frisbee, a solid frisbee. It doesn't have any holes in it. It's just a solid three-dimensional shape. Where a washer, when you think about like building things and you use a washer, it has a hole in the center of it or somewhere in it where there's a gap, right, of material being used. And so that's the distinction between a washer and a disc, okay? Now, this is the definition that we have, and instead of having a function, what we now have here, this is cool, I'm going to use my laser that I now know about. Look at this, it's A of x, and A of x is the area. So now, when we did problems in the past, it was a function, so it was a one-dimensional thing. And then when we did the integral, we found the area under the curve, which gave us a two-dimensional thing, right? So we went, by taking the integral, we went up a power. So now, because we have area, when we take the integral, what that's going to end up giving us is a volume. Does that make sense to you guys in terms of what I'm saying with the integral? Integral of area gives us volume. Integral of a curve or a line gives us area. If we were to take the integral of a volume, we'd end up in the fourth dimension. I don't know what to call that. But we can do math at those higher levels, which is strange. But what we're going to be doing today is building on that. Okay? So let's do this first example and go from there. Okay. So this first example tells us to find the volume of a solid obtained by rotating about the x-axis the region under the curve y is equal to the square root of x. And it's giving us the region that they want us to do it from. It's from 0 to 1. So with these problems, I'm always going to want you guys to graph them, okay? So I'm going to graph it kind of big so you guys can see. So I'm going to call that one and this one. And so here's the origin. So when x is 0, y is 0. And then when x is 1, y will be 1. And since we know it's a radical, we know it's going to be some sort of curve, right? It's going to be some curve that looks like this. And we want this thing, it's going to be bounded. It's going to be bounded with the x-axis. So that's important for us to know. It's bounded with the x-axis because the area is going to be to the x-axis whenever we only have one curve. And then it's going to also be bounded by x equals 1 because that's where we're restricted in terms of the domain of the area. Does that make sense to you guys? So if you were to do this on your calculator, right, you'd end up finding, all right, this is the shaded region, and we would get the area of that thing in particular. Now, the new interesting piece to this is that we're going to rotate this thing about the x-axis, okay? Now, when we're doing this, since we're rotating about the x-axis, whenever we use the disk or washer method, what's going to end up happening is this. We are always going to have our slices, our cross-sectional slice that we did from 6.1, is going to be perpendicular to the axis of rotation. So, if I'm perpendicular to the axis of rotation, what should be my cross-sectional slice? Should it be a vertical one or should it be a horizontal one? What do you guys think? And please, you can speak through the mic if you want. Julian said vertical question mark. Since we're trying to be perpendicular to the x-axis, it's going to have to be a vertical slice, right? So our slice should come this way. So that cross-sectional slice is going to cross which axis? Correct. And since it crosses the x-axis, we know that we're going to integrate this thing with respect to x, and so it's got to be a dx. Okay? Now, some information for you. What's going to end up happening here, and it's important you guys see this, we're going to, if we rotate about the x-axis, right, it's just the curve that's being rotated, and then we're going to fill in the area, right? So when I think about this, I'm going to be forming, and I'll do this in red so you guys can see, I'm going to be forming what is that? At that cross-sectional slice, you end up seeing that the height of the function to the x-axis is what? To that shape that I just drew.
Is it the radius?
That's exactly what it is. It's the radius. So I see that the cross-sectional slice ends up becoming the radius. Or the function, the height of the function is the radius. Now, we're going to have a bunch of circles created, right? So here's a circle. If I used the endpoint, that would form a circle. Over here would be another smaller circle. There's circles everywhere because that cross-sectional slice can slide anywhere from 0 to 1, correct? So here's the formula for the disk method that's important. So the disk method is the integral from a to b of f of x, that quantity squared dx. But since we're looking for the area of a circle is what, my friends? And in fact, I can even change this. I'll change this real quick. What is the area of a circle? Can someone tell me?
Is it 2 pi r?
That's the circumference. Julian, is that supposed to be a square? Yeah. So remember, area of a circle is pi r squared. So this f of, I should call this f of x because I don't want you guys to mess this up. This f of x is the radius. I'm squaring it. What do I need in my integral? For the area. Don't I need pi? That's right, I need pi. So I want to write that clean. I want you guys to be able to see it. So the integral is going to go from a to b of pi of my function's height squared dx. That is what the disk method will be, where f of x ends up being the radius. Okay? So in this problem here, what we're going to end up having is the integral from 0 to 1 of pi times the height of the function, which is the f of x, squared dx. So pi is just a constant, so I can bring that out front. I'm going to go the integral from 0 to 1 of x dx, and that's going to yield x squared over 2, that times pi, evaluated from 0 to 1, is going to give us 1/2 pi, right? Units, what kind of units am I going to have? I love that you guys think squared. What are we going after? Yes, we're going after a volume, and so this is a cube because when we look at this is a circle, right? This thing right here is a circle, but it's like I don't know if you guys remember what these things were. You might be old enough because you're college students. We used to have CDs, right? If you just think of this as a solid CD with no hole in the middle, if I stack a bunch of CDs together, didn't they eventually form, yeah, that is funny, Jason. Didn't they eventually form what looked like a cylinder? They formed a volume, right? So just think of this as a bunch of circles being created. And so I'll use a different color to kind of demonstrate that. So if this was the radius here, this guy would be a circle right here. This would form a circle, maybe bigger, here. And then you just see that there's a bunch of circles that are being created that are going to be stacked and stacked and stacked. And then we end up with a volume, right? And we end up seeing that the curve, that area between 0 to 1 ends up being this solid structure. But each one of the cross-sectional slices is forming a disc, hence the name for this thing. Does that make sense? Okay, so I got one person to say yes. What about the rest of you? You can click on the yes in the participation thing too, just so I can see. Remember I told you guys that if you don't want to speak up, you can also do it that way. I just want to be able to get a feel of, am I going too fast, or are you getting what I'm saying? Because I could finish this in 10 minutes, but that means nothing if you're not picking up on the information. Okay? Okay, so let's look at the next example. And the next example, it's asking for us to find the volume of the solid that is being rotated, that's rotating the region bounded by y is equal to x cubed, y is equal to 8, x is equal to 0, and then we're going to do that about the y-axis. So here it is. I'll graph the cubic. So 0, 0, 1, 1, 2, 8. And then, so this curve is going to look something like this. Right? That's the cubic. Then it says y is equal to 8. I'll do that in a different color. So y is equal to 8 is this function here. Terrible. Right, that's y equals 8. This function here was y is equal to x cubed. And then the next function that they ask for is x equals 0, right? So x equals 0 is along the y-axis here. And so the area that's bounded ends up being this thing right here. So this solid, or I'm sorry, this area is going to be rotated about the y-axis, right? So we can think of that shape being wrapped around in a circle. And so the important question here is, do we do a horizontal or a vertical slice? Yes, it's going to be a horizontal slice, and it's going to go this way. Now, important thing to talk about is in the previous problem I said, oh, it's a disk method, right? And I kind of took it for granted why it was a disk method. But the reason that this one was a disk method was there a gap at all to the x-axis? So the shaded region, was there a gap there to the x-axis? So looking at this thing here, this blue here, this blue shaded area, was there a gap anywhere along this x-axis here? Since there's not, that's a disk method. If there is a gap, then we have a washer. Okay? But since we have no gap, we'll do disk. So going back to our next problem, we're rotating about this axis here. Is there a gap in that shaded blue region? What do you guys think? Is there a gap here? Is the blue not hitting that axis at all? Yeah, it's not. And since it's not, that tells us this has to be also a disk method problem. Okay, now let's see if you guys are understanding what's going on here. So the volume is going to be equal to the integral from where to where? Is it from 0 to 2? Or is it from 0 to 8? Julian says it's 0 to 8. Do you guys agree? Crickets. Come on. So it's going to be from 0 to 8. And the reason that is because my cross-sectional slice is going to cross the y-axis. And so we're talking in terms of dy. So our bounds have to be in terms of y. Okay? This problem here, interestingly enough, and I'm not going to do it, but if I were to rotate about the x-axis, then it would have been a dx. And the volume isn't the same, which is interesting. Because the thicker slice of it is traveling a much greater distance because the radius is so much bigger. I can do it after for you guys, but we're in a dy because my cross-sectional slice is crossing the y-axis, right? So we have to do it in terms of y. And then just so you guys can kind of see the picture of what's happening, this thing is going to form, and actually I'll do it in a blue. Right, it's that circle that's occurring there, stacks of them. So tell me what I need to write. I'll do the hard part. I need pi. What else do I need? Well, f of x, but it's not f of x this time, Jose, because we're in terms of y, we need the height of this in terms of y. So the function, right? This function here, we know it to be x cubed, but we need to write it in terms of y's. And so I need to solve that out to see what that is, right? So y is equal to x cubed would become the cube root of y is equal to x. Okay? So then the function that I need here is the cube root of y, that squared dy. Are we okay with that?
So the function's always going to be squared?
Yes, because in the disk method, so in the disk method, if we go back up here, this is the formula for it. Because
it applies for like dy dx, right?
Correct. So whatever the function is, it's going to be that, because the function is going to represent the radius, and so the radius must be squared, because we have to remember that this piece right here, it's cool that I can use this laser, it really is. This right here represents the area of this circle that's being created. Does that make sense?
Yeah, thank you.
Yeah. And so look, one circle, a bunch of circles being made. If they're all stacked on top of each other, they're eventually going to form this solid state. And so this is the formula for washer. Okay?
Okay, cool.
Cool. Thank you for asking. I appreciate it. It makes me teaching much easier.
Yeah.
Okay. So then from here, when I go to integrate this thing, what I always try to do is I like to make it in terms of powers. So I'm going to go from 0 to 8. I'm going to bring the pi out front because it doesn't have y in it. And I'm going to have y to the 2/3 dy. Does everyone agree with that? We're okay? Just making sure that you guys can translate that. Okay, so then when we do the integral here, I'm going to get y to the 5/3 with a 3/5 in front. Let's not forget to multiply by pi from 0 to 8. So what this ends up being is 3/5 pi times 8 to the 5/3 minus 0. So I'm just going to leave that piece out. And so I'm going to get 3/5 pi times 32, which will yield 96 pi over 5. And then again, units cubed. We okay with that?
I had a question. Where'd you get the 5/3 from?
Oh, okay. So when we do the integral there, right? If the power rule that we do, don't we add 1 to it? So the power rule that I'd given you when you do the integral is n plus 1 over n plus 1, x to the n plus 1 over n plus 1, right?
Yeah.
So then in our problem, we're going to get y to the 2/3 plus 1 over 2/3 plus 1. But isn't that 2/3 plus 3 over 3? That's a terrible 3.
Yeah. Oh, okay. Yeah.
Make sense?
Yeah, I see it.
Okay, cool. Good. And so this is what the disk method is. It's not too bad, right? It's a matter of being able to graph the function, see the picture, and then decide which way my cross-sectional slice is going to go. But the cross-sectional slice is always, 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 with the disk method, perpendicular to the axis of rotation. I can't stress that enough. The disk method, the cross-sectional slice, that red line that I drew there, is going to be perpendicular to the axis of rotation. We okay? Okay. Now, this next one, let me go ahead and graph this thing so you guys can see. And it tells us that we have the region R enclosed by the curves y equals x and y equals x squared. So here's my x-axis, here is my y-axis, and I'm calling that 1 and that 1, so that would be 2 and that would be 2. So my line y equals x is that guy right there. Agreed? That is the y equals x squared, and obviously I'll just keep going with that so you can see. Something like that. Now the region that's bounded, is this right here, correct? Now, what am I rotating about? What axis? We see it's the x-axis, right? And since it's the x-axis and this is the axis of rotation, do we see a gap in the shaded region to the axis of rotation? Yes, and since we see that gap, this tells us that we should consider the washer method. Okay? Tomorrow or our next class session, I'll talk about what's called the shell method. And the shell method could be used with these problems also. So we'll get into that. Now, the washer method, the formula for it is going to be this. It's the volume is the integral from a to b of the outer radius squared minus the inner radius squared and I'll call it dr since we're talking about radii, and then that multiplied by pi, right? Because each one of those is the area of a circle, right? It's basically the area of the outer circle minus the area of the inner circle. Does that make sense? Okay, so our cross-sectional slice here, since we're going about the x-axis, both washer and disc are going to have cross-sectional slices perpendicular to the axis of rotation. So that tells me my slice has to be a vertical slice. Okay? And what's really happening here, and I want to stress this to you guys, it's the, and I should do it I'll do it in a further spot, so it's more obvious. So if I did it here, right? The outer radius is going to be that purple part, right? The inner radius is this piece here. It's from the inside piece. So that purple one is the distance to the x-axis, right? Of y equals x. And the green one is a representation of the distance of the y equals x squared to the x-axis. And we're subtracting those to get the area that's in between the two curves, much like we did in 6.1, correct?
Oh, wait, which one's inner, which one's outer?
So in this case, the outer is the one that's further away from the x-axis. So that would be the y equals x. Right? So I'll blow it up so you can see. So this here is further, it's bigger, it's further away from the axis of rotation. Does that make sense?
Yeah.
And this one here is the inner piece. So this distance minus this distance, each one of them squared, is going to yield this inner piece, right? Because then when we rotate, what ends up happening is we're going to have, well, it's what they do in bars. So in a bar, you guys don't know this, but if you go to bars now, what they do with their glasses is they'll make like martini glasses and things like that. Bear with my drawing. So this is, let's say this is a martini glass, right? What you don't see is what they do with their glass is they'll do this. Oh. So from the outside where you're holding your glass, I don't know if you guys can, if my picture is very good. I'm trying to make a decent picture, but it's probably not that good. If you look at the outside of the glass, it looks like it has a lot more volume in it, right? But when you look at the glass from the inside, they've shaded away part of the volume by making the inside of the glass curved. Do you guys see what I'm drawing there? Does it make sense?
Yeah.
Okay, cool. So what's going on in this picture that I'm drawing for you, the wine glass that I've just drawn there, just think of it as taking off the legs and it being on its side, where this would be the x-axis. Does that make sense?
Yeah.
Okay. Cool. Just trying to give you like some... I mean, it's so funny how things are done now. I think I talked to you guys about cereal, right? If you go to the cereal stores or you go to the grocery store and you look at cereal, they're still the same height as they used to be, but they're way thin compared to what they were when I was a kid. When I was a kid, they were like 3 inches thick, and now it's like 1 inch thick. It's crazy. So they deceive you by like having the box. When you just see the area of the box from the front, you still think you're getting the same amount of cereal, but it's not. Okay, so enough of that. Let's do this problem. So we need our bounds. What should our bounds be for this problem? Okay, so before, because it's going to be right either way you talk about it. So is this going to be a dx or a dy problem? Yeah, it's a dx. And so the bounds have to be in terms of x, right? So my lower bound is this first intersection point here, which is 0. And my upper bound is going to be this 1, because that's the right side. Yeah, correct, Jose. So I'll put pi, but I'm going to move pi out front already. And then what is my outer function in this case? Isn't my outer function the y equals x? So I'm going to get x squared minus the inner function, and the inner function for us was x squared, but I have to square it. Are you guys okay with that? So then what I'm going to get is pi times the integral from 0 to 1 of x squared minus x to the 4th dx. And so the integral is going to give me x cubed over 3 minus x to the 5th over 5 from 0 to 1. And all of that's being multiplied with pi. So I'm going to get pi times 1/3 minus 1/5. And then obviously the 0 is going to drop away. And that's going to yield 2 pi over 15 units cubed. Are we okay with that? Does anyone need clarification on those numbers? No, we're good? Okay, cool. Then let's go on to the next example. And now I'm going to make things even harder. Okay? It's time to make a little bit of a jump. Now, look. We have y is equal to x and y is equal to x squared. So that's the same function that we just had. But instead of rotating in the previous problem, we rotated about the x-axis, right? Look what we're rotating now. We're rotating about y equals 2. So I'll draw my curve so you guys can see. There's that guy. And then I'll use pink. It says that we're going to rotate this thing at y equals 2. So y equals 2. Terrible. I want it more accurate than that. You get it. So that's my y equals 2 line right there, right? That is going to need my axis of rotation. So, what kind of slice do I have? Is it vertical or horizontal? Yes, it's going to be a vertical slice. Oh, someone said horizontal. It's vertical. It's vertical. And here's why it's vertical. Remember, the cross-sectional slice always has to be perpendicular to the axis of rotation. That's the critical piece. It's got to be perpendicular to that y equals 2. Now, here's the weird thing. Is this a dx or a dy? What do you guys think? Yeah, it should be a dx. And the reason it's a dx is because that cross-sectional slice, if I were to extend it, right? Which axis does it cross? Does it cross the x-axis or the y-axis? It crosses the x, and so because of that, it's a dx. Does that make sense? Julian, are we okay with that? Just making sure that you get that. It's important that you get it. Okay, cool. Okay. Now, where's this thing bounded? because we're going to need that to find our integral. Where is it bounded? From where to where? In terms of x, right? Where is it bounded? And maybe you guys are not understanding what I mean by bounded. That might be possible. Where do they intersect? Yeah, they intersect at 0 and at 1. And so those are the bounded regions from 0 to 1. Is that a better way for me to ask it? Where do they intersect? So you guys can see it? Okay. Sorry, I like I said, I get caught up with math talk, and so the bounded regions are where they intersect, where it closes them off. Okay. So we need pi. I'll always just put out front. And what is the outer function now? From the radius, from the axis of rotation. Yes, it is the x squared. So the x squared is actually further away, right? So from here to here is further away. But to write that radius, it's going to be 2 minus x squared squared. Minus 2 minus x squared dx. Does that make sense to everybody? All right, good, cool. So then in order to do this problem, we have to do some algebra, and yay, here it comes. So the volume is going to be the integral from 0 to 1 of 4 minus 4x squared plus x to the 4th minus 4 plus 4x minus x squared, and all of that times dx. So what do you want me to explain again, Julian? Sorry, I just missed that. How I got the radius? Yeah, okay, no problem. So look at it this way. So from here to the x-axis is what I'm looking at, right? So the radius, if I were to rotate this at y equals x, I always rotate to x, right? To the x-axis. So how far is it from the pink line to the x-axis? 2, perfect. But I have to bounce back up to the blue curve. So that means I have to go 2 minus the x squared function. And that's why my radius is that. Now for the other one, it's 2, and then I got to bounce back to x. So it's going to be 2 minus x. And that's going to give me this radius here. Does that help clarify it? Okay, cool. See how cool the laser is? Oh, I love it. It makes it so much easier for me to explain. Oops. Okay. So now let's see if we can eliminate some things, because that might be possible. It looks like 4 can go with 4. And then there's just a combination. So I'm gonna get pi integral from 0 to 1 of x to the 4th minus 5x squared plus 4x. Right? And so now when I do the integral, I'm going to get x to the 5th times 1/5 minus 5x to the third over 3 plus, and I'll just write it so you guys can see, over 2 evaluated from 0 to 1 times my pi. So I'm going to get pi times 1/5 minus 5/3 plus 2. And I just, for thorough sake, 3 over 15 minus 25 over 15 plus 30 over 15 will yield 8 pi over 15 n units cubed. We okay? Any questions on this one? Awesome. Good, 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 good. All right. Let's use that same picture again, but now mess with you in a different way. All right, here we go. Jose, that's funny. Okay, so there's my y equals x. There is my y equals x squared. But now it's telling me that my axis of rotation is at x equals a -1. So, please tell me, what is my cross-sectional slice? Horizontal or vertical? It should be a horizontal slice this time, right? So our slice should go this way. Now, that tells me then, is it going to be a dx or a dy? Yes, it's a dy. Now, what I should have done on the previous problem, and I'm gonna ask this time, is there a gap for that shaded region to the axis of rotation? Since there's a gap, that tells us what method should we use. Good. So this should be the washer method. I should have asked that up here. I just did it. My apologies. Again, it's me making assumptions that I shouldn't. So it's the washer method. So that means we need to have an outer radius and an inner radius, correct? So please tell me what you think the outer radius will be. And remember, it has to be in terms of y in this case, because our integral is a dy. Square root of y. Okay, very close, very close. Now, think of it like this. From here to y, to the y-axis, is how far? Yeah, plus this distance from here to here, from the x-axis to the blue curve. So the distance from the y-axis to the blue curve is that square root of y, correct? So then that means that the distance from here to here is 1 plus the square root of y. Does that make sense? Let's not forget our pi. We need to subtract the inner radius. So tell me what the inner radius should be then. That's it. It's going to be 1 plus y squared. Very good. Now, here's the thing that's so cool about this. When our slices are to the left of our functions, like this, left of the axis, we're going to add. If I'd have had my slice here, it would have been the radius minus the function. So like in this example, it was above it. So it was 2 minus the function. If I had done it down here, it would have been 2 plus the function. Does that make sense? Okay. Yeah, because here, the distance to the x-axis would be 2, right? So it would be 2 to here, and then plus the outer function. And notice, it also changes what the outer function is. So here, if this was the axis of rotation, the outer function now is this one, right? The y equals x. In this one, the outer was the blue. So it swaps which function's on the outside, which function's on the inside. So in this one, the outer function is blue, but if I had rotated over here, the outer function would have been the black y equals x function. Does that make sense? All right, good. So then we need to do math again. Terrible. So we're going to go pi integral. Oh, and you guys, what are the upper and lower bounds, or where is the intersection occurring in terms of y? Perfect. So our integral is going from 0 to 1. So from 0 to 1, and then let's do this expansion. I'm going to get 1 plus 2, and I'm going to go y to the 1/2 because I want to use powers, plus y minus 1 minus 2y minus y squared dy. We can clean that up. So from 0 to 1, I'm going to get 2y to the 1/2 minus y minus y squared. Do you guys agree with that? Okay. So then when I do the integration piece here, I'm going to get pi times y to the 3/2, so that's going to become a 4/3, minus 1/2 y squared minus 1/3 y cubed, evaluated from 0 to 1. And so I'll get pi times 4/3 minus 1/2 minus 1/3, and that should clean up to give me my answer of pi over 2 units cubed. Do you guys agree with that? We're good? Okay, so here's what I want to do, or you guys tell me what you want to do. I want to give you guys 2 problems to try, and then I want to do them. Do you want me to record that while I'm giving you time to do them? Or do you want me to just stop the recording and then do the problems? Either way is fine with me. I guess people can fast forward videos, I guess. Okay, let's just keep recording so you guys can look at this. All right, so I want you to try this. So y is equal to 1 over x. Y is equal to 0. X is equal to 1. And x is equal to 3. And I want it to be rotated about y equals a negative 1. So the big thing is, you need to be able to graph this, right? So try to graph it and just do the setup, and then I can do the work for you guys so you guys can see. I'll give you guys 3 minutes, okay? All right, let me go ahead and try to graph for you guys, at least that piece. Okay, is that the picture that you guys got? So that should be the shaded region, correct? Okay. And then the axis of rotation is at y equals a -1. So this is the axis of rotation. We're good? Okay. Tell me about the cross-sectional slice then. Vertical or horizontal? Good. There's a slice, so that tells us what kind of integration are we going to have, what variable? Good. So we know our integration is going to be a dx. Very, very good. Now, what is the outer radius? And I'll write it here just so we can see it still. What is the outer radius? Very good. So it should be 1 plus 1 over x. What is the inner radius? Good, it's 1. And so, I should have said this, but I gave it away. There is a gap, so this is the washer method, correct? Okay. So now when we set up the integral, what are the bounds from where to where? Very good. So we said the outer was 1 plus 1 over x, that quantity squared, plus 1 squared dx. And that's the setup integral, correct? Do you guys agree? Okay, so then expanding this thing, I'm going to get, all right, pi integral from 1 to 3. I'm going to get 1 plus 2 over x plus 1 over x squared minus 1 dx. That will become the integral from 1 to 3 of 2 over x minus 1 over x squared. Ooh, I'm sorry, plus 1 over x squared dx, because the 1's will cancel. And that's going to give me, when I take the integral, I'm going to get 2 ln of absolute value of x minus 1 over x evaluated from 1 to 3. which is going to give me pi times 2 ln of 3 minus 1/3 minus my apologies, 2 ln of 1 minus 1, and I'm trying to show this to you guys so you guys totally see it. So I'm going to get pi 2 ln of 3 minus 1/3 minus 0 minus 1, and so I'm going to get I'll clean it up right now. Pi ln of 9 plus 2/3. And of course, this is units cubed. Are there any questions with this problem? All right. Okay. Cool. All right. Do you guys want to try one more? I'd like to give you one more, if that's okay. Okay, so here we go. Let's say y is equal to the square root of 25. 25 minus x squared. Y is equal to 0. X is equal to 2. And x is equal to 4. And I want it rotated about the x-axis. Okay, go ahead and try that for me. Are you guys ready for me? So then, let's do this. 1, 2, 3, 4, 5. 1, 2, 5. I only need that section of it because of, well, I'll use colors for you guys to see. X equals 2 is a line. X equals 4 is a line. And I'll use purple. Y equals 0 is a line. So we have this line right here. Right? So the region that's bounded is this one right there. Do you guys agree? Okay, so cool. Our cross-sectional slice should be which way if our axis of rotation is going to be here. Cool, good, good, good. It's a vertical slice. So we have a slice that's going this way. And that tells us perpendicular or vertical, or I'm sorry, dx or dy? Perfect, it's a dx, good. Now, washer or disc? It's a disc, right? There's no gap to the axis of rotation, so we have a disc. What are our bounds? Perfect. 2 to 4 pi, that's volume, and our function is 25 minus x squared, that's squared dx. Okay, so then that's going to give us an integral that's going to go pi times the integral from 2 to 4 of 25 minus x squared dx, which is going to give us 25x minus x to the third over 3, evaluated from 2 to 4, and then let's not forget to multiply by pi. And that should give us 100 minus 64 over 3 minus 50 plus 8 over 3, which I can clean up a little bit to be 50 minus 56 over 3, and that is 94 pi over 3 units cubed. Does that make sense? Okay. Any questions on this at all? No? Okay. I'll stop the recording